Okay, we're going to discuss ellipses. This is part 1. This is in section 9.3. All right, an ellipse is what a lot of people would call an oval. It has a lot of things in common with a circle. You could think of a circle really as a special kind of ellipse if you would like. Now, if you start with the formal definition of an ellipse, it is the set of all points that meet certain conditions. Just like a circle had a similar definition. It was the set of all points that were equidistant from a given point with a given radius. In this one, it's going to be the set of all points that the sum of the distances to two fixed points is always the same. So they will give you, to begin with, two fixed points. Each one of these is called a focus. So I have like F1 for this example is this point right here, 4, 0. The other focus, F2, is the point -4, 0. So you're given these two fixed points called, in plural, the foci. So you have those 2 points, and then you're given a fixed sum of distances. So for this one, I made it 10. So the sum of the distances from any point to each focus is going to be 10. So if I pick a random point on the ellipse, if I measure its distance to focus 1, that's your PF1, and I measure its distance to PF2, that's PF2, the sum of the distances will always equal 10. Okay, so that's the formal definition. You're given the two foci and that fixed sum of distances. Now, if you just work with this, the distance PF1 plus the distance PF2 equals 10, you will come up with this equation. So here's where I used the distance formula for each one, added it together, said it would be 10. All right, we probably won't work with this very much, but that is formally how you would start. And if you just manipulate this around, do a lot of squaring and rearranging, you can get it to this form right here. And this is the standard form for the ellipse that we see above, the standard equation form, I should say. X squared divided by 25 plus y squared divided by 9 equals 1. This is a great form, and you might think, well, I don't really like it because of the fractions, but actually the denominators tell you a lot. 25 is the square of 5, and 9 is the square of 3, so we've got some nice square numbers here. But anyhow, 5 and 3, those are key numbers when it comes to this ellipse. If you look up here, the long ways on this one, we call this the major axis. This point over here is 5, 0, and this point over here is -5, 0. So those are what we call the vertices, and they're located at 5 on the x-axis. So you can see the connection, located at 5 on the x-axis. And then if you look here on the y-axis, there's two other points that are located with 3, right? And you can call these points that are on what we call the minor axis, co-vertices. Not every textbook and author will use that term, but I do like to give them a name. So this point up here is 0, 3, and this one down here is 0, -3. So basically, those are the numbers at the far edges of your ellipse. So this equation will tell you how far it goes, all right? Now, just real quick as a kind of visual check, if we check the 1.50 and just look at the sum of the distances, PF1 plus PF2, you can see how it does equal 10. So if I am looking at this point right here, its distance to F1, see, I picked this point because you could just measure it horizontally. 5 plus 4, that's 9. And then this point's distance to F2 is 1. And 9 plus 1 would be 10. Okay, now let's just look at the standard form of the equation a little bit more. There's two ways your ellipse can be. One way is the major axis could be horizontal, and that's what we saw in the last case. The other way is the major axis can be vertical. So we'll just look at each one of these quickly. They're very similar. So if the major axis is horizontal, that means it's going long ways along the horizontal axis. Now I am drawing all of these where the center is the origin to begin with. All right. My ellipses are not too great. You'll just have to freehand them as best you can. Okay, so in general, here's the standard form. Right. Your textbook uses the convention that A is always greater than B. Okay, so A is greater than B, so A squared is greater than B squared. So the larger number is underneath the x squared, and that means then that these points here are going to be farther from the origin or the center than these 2 points. Okay, well anyhow, when you have this is your equation and you have a squared here, the vertices are going to be at a comma 0 and negative a comma 0. So here's a0 and then here's negative a0. And then the co-vertices are going to be at 0b and 0 negative b. Okay. Now, we're not going to talk too much more about the foci today, but we use the letter C for the foci. They're going to be on the major axis between the center and a vertex. So here's the center, here's a vertex. The focus will be approximately here. So that would be C comma 0. And then the other focus would be over here, negative C comma 0. Okay. All right, now, if the major axis is on the vertical, it's going to be taller going up and down. Okay, again, we're going to just stick for now with the center being the origin. Here will be the equation, right? Now remember what I was saying, they're always going to have A greater than B. If you go looking around the internet at ellipses, you may not always find that observed, but in your textbook it is. Okay, so if A is greater than B over here, the larger number will be under the y squared, and that will tell you that it's going to run longer on the y-axis. It works out pretty nicely, actually. Okay, now in this scenario, the vertices then are going to be on the y-axis, so that's going to be a vertex up here at 0 comma A, and then there will be the other vertex down here at 0 comma negative A. And then on the x-axis, that's where we'll have the co-vertices. So it'll be B comma 0, negative B comma 0. And then the foci, they're on the major axis. So since the vertices are on the major axis, that's where the foci will be. So we're going to have, here's one of them, 0C, and then here's the other one, 0 negative C.